together. Would you like to just say a quick thing about background?
Sure. Good afternoon. My name is Wes Garland. I'm the CTO at King's Distributed Systems. I have a long and varied background in this and related industries. I've delivered a pile of telecom-grade software systems and hardware systems. And I've been involved in server-side JavaScript research and development for a little over a decade now, which is how I arrived at KDS. What we're doing here is really, really, really interesting.
Perfect. And then
sure. Thanks, Dan. I'll give you a bit of a history of how this whole thing came about. I do research in astrophysics, and I'm specifically interested in how galaxies like the Milky Way form and evolve. And it turns out that a really powerful way of trying to understand that is looking at how the gas and the stars in the disk of a Milky Way-like galaxy orbit around the center of the galaxy. And that, if you think about sort of the really simple laws of gravity, the faster that gas moves, the more matter has to be enclosed inside that orbit. And it turns out that in galaxies like the Milky Way, most of the matter, and therefore most of the energy, is in dark matter. It's in a form of matter that we can't see. And so the idea is to use the gas and the stars, which are things that we can measure, as a proxy for the things that we can't measure and that drive galaxy formation and evolution. So in a big picture, that's what I'm interested in. And one of the things that's happened in the last couple of decades as telescopes have gotten better and better is that we've been able to make more and more sophisticated measurements for more and more galaxies in the local universe. And what that means is that there's the computational burden of modeling those galaxies has gone up and up. And so in the last couple of years, we've devoted, my research group has devoted a lot of energy into trying to model the distribution of gas that we see in the sky. So translating what we observe, which for the technically minded folks are Doppler shifts of spectral lines, into orbital velocities. In other words, what we're trying to port what we measure into physical properties of the galaxies that we can then do our science with. And that involves running a series of multidimensional models for each galaxy. And so I've now had a couple of students who have worked on this problem. And in the last couple of years, we've been in the situation where our ambitions as scientists and the samples that are available to us outweigh the computational resources that we have to evaluate those models. So for example, my PhD student, Colin Lewis, who just finished his PhD at Queen's last year, was limited, the HPCVL at the time, resources that he used to carry out both his master's and PhD theses, limited him in terms of the sample of galaxies that he could analyze. And so we decided that about a week of runtime for a standard HPCVL allocation was as long as he could tolerate in terms of setting his sample size, because having to wait any longer than that meant that we couldn't do science at we risked not being able to repeat the experiment enough times to get scientifically valid results. And so one of the things that underpins a lot of the research that we do is this program called DiskFit, which Dan has now worked with, Dan and his team has now worked with. And Dan will be the first to confirm, and others on his team, that scientists are not computer programmers. And so this code, while it did what it was supposed to and was giving us the science that we needed, was not written in a way that was either efficient or portable to the larger scale problems that we were trying to address. And so a combination of having some great ideas and access to wonderful samples of galaxies combined with our poor programming skills led us to partner with Dan to develop a solution to try and increase the computing capacity to which we had access. And this is really how this project was born. And the early tests that we did with our group suggested that using a tool like the one you're about to see would increase our capacity to model galaxies both differently as well as larger samples of galaxies by such an impressive number that my student's PhD thesis would have been totally different with this kind of technology. And so what you're going to see is my poorly written Fortran code transformed into a beautiful piece of work by Dan's team and running on multiple platforms in a way that we couldn't achieve with HPCVL at the time. I'll stop there.
Christine, thank you so much. Okay, so I'm going to ask KC to share his screen and run us through the demo, and I'll explain quickly some of the features of what this platform enables. So I see that it's showing up properly on your screens. So it's showing up on mine. This is just a website, diskit.apps.distribute.qt. Any one of you right now could navigate to this application no download, no install, accessible anywhere. So Christine can share this with any of her students or collaborators around the world by literally sending a URL. So that's step one in terms of an advantage, in terms of sharing scientific applications and accessing knowledge that other researchers are creating. If we scroll down a little bit, I mean, obviously this is not a command line interface, which we've become used to. This is now a nice, slick UI. So it's a website. You can make this as visually rich and stimulating as you want, and as easy to use, as low or no code as you want for people who are more interested in the science and less in the programming. We've implemented a drag and drop box or browse box where you can upload the Galaxy files that Christine was just mentioning. So here we're uploading well, everything you require to run this computation, including a key store. So that last part I'll talk about perhaps a little bit later. This is the password to unlock that key store. And now we can perform as many bootstrap realizations as we wish. So what this means is we're performing calculations in parallel. These bootstraps, essentially, if I recall from Christine's presentations correctly, we're going to scramble the residuals and repeat the fits over and over and over again to create a distribution that gives us the uncertainty that goes along with the results, which is critical for producing credible scientific results. Once that's done, I think we're going to set it at 1,000. Let's do 2,000. Let's do 2,000 bootstraps. Thanks, Casey. And before hitting the compute button, we'll hit that little triangle on the right, which gives us a couple of extra buttons. So here we're setting it to the demo scheduler, but I'd like you to notice that we've added optional burst buttons that we can activate or deactivate as we see fit. So the idea here is that any researcher will be able to log into their campus's aggregate compute power that's all linked through a convenient distributed computer screensaver. But if they want to throw $5 at it and burst onto AWS or any third-party resource, they can make the problem. They can add 1,000 cores or whatever they want to make the problem finish today instead of tomorrow, or so on and so forth. So here what we'll do is we're going to leave the buttons deactivated, and we're going to show how they can also be activated on the fly, midway through the computations, and also deactivated midway through the computations. So let's hit compute. So what it's going to do is it's going to run through the initial set of calculations locally. And so now what you're looking at, and Christine, please jump in if I butcher your research here, but we're looking at velocity in kilometers per second of the stars as we progress radially outward from the center of the galaxy. Once the first set of computations is done locally, now it's sending it off to the network to do those 2,000 bootstraps in parallel. So right now, I believe with the help of Queens, we have about 40 or some odd computers that are connecting to our scheduler and saying, hey, I'm ready for work. And what's going to happen is the network is going to distribute those slices. It's going to perform, I think, 1 or 2 tasks first. And as it comes back, it says, yep, this is not a broken job. They're going to just essentially burst out onto all the other devices. So you can see it's already picked up 113 of these slices in parallel, like that. And all Christine would have had to do is drag and drop her data and press compute. And optionally, there's that little cloud button that you see in the top right next to the cancel button, where we can say, you know what, let's give this a little boost and let's turn on AWS, for example. And we could turn on Circle if we wanted, so on and so forth. And you can see that all of a sudden it jumped up to 227. So AWS now, without even thinking, it just spun up a bunch of workers and is now working on computational astrophysics. No fuss, no muss. And so as these compute, I'm going to hand the floor over to Wes to talk a little bit about the underlying system and the advantages of a web-based platform. But you can see how fast this is going. We're already at approaching a quarter of the job done. And there's only 40 or so computers at Queens. If there were 2,000 computers, they would theoretically just all pick a slice, all work on in parallel, and be done. And Christine would be done her fit before finishing her first coffee. So Wes, can I hand it over to you to talk a little bit of, within the time remaining, a little bit about DCP and what's under the hood here?
Sure. DCP is essentially a framework for generating distributed compute, for doing distributed compute work in the web platform. So the web platform is very important in today's tech landscape. It's essentially the single place where we can turn around and build software and both expect it to work pretty much everywhere, and most importantly, continue working pretty much everywhere. The committees that steer the web have been working very, very hard for the last couple of decades in a commandment they have, which is thou shalt not break the web. Because if you change a standard in a web browser in a backwards incompatible way, you literally break tens of millions of abandoned but useful websites. Some useless ones too. The web technology stack is essentially growing in both capability and in performance in leaps and bounds. It's the fastest growing ecosystem and capability platform out there. And it's actually the platform that just about every developer is familiar with. All the young guys are taking up on it. And one of the great things about this platform as well is that we get a lot of free R&D out of Microsoft, Apple, Google, and so on and so forth. And Dan is reminding me to talk about security. And that's actually super, super important. So the engine that we run this in currently, when we're doing our Windows workers or our enterprise grade workers, is a V8 interpreter that was developed by Google. And that is the actual JavaScript engine that is in use in Google Chrome, Brave, and a few other web browsers out there. So from a security point of view, we actually get to build on top of that super tight web security sphere that we have today, because we have to think about, the types of work that's being done on remote systems and on desktops where you don't necessarily know the person deploying the job. And the type of work we're doing is actually exactly equivalent to just surfing to a web page. So from that point of view, what we're doing is just like surfing the web, except we're accelerating science, innovation, and research. So I got probably another 30 seconds to talk.
Actually, it's we're about to wrap this up.
We're at 1994. We're almost done. 1995, 97,
98.
So there's probably going to be some straggler out there that makes us wait for a minute. 1999, or let's party like we're Prince. And yeah, so essentially what we're doing is we're looking at a finished job. So when was the last time you ran a 2000 slice disk fit that fast?
Never. I think the relevant question is, when have we ever run a 2000 bootstrap iteration? And the question is, the answer is almost never. Just to give you a sense of scale, my PhD student had to stop at 100 iterations per galaxy, so a factor of 20 less, and that was because of limited compute power. So this is truly a huge step forward in terms of compute capability. And with that 100 bootstraps, it took him a week to run his sample through the high performance facilities available at Queens at the time. This was as of, I guess, about 2 years ago. And so the leap here is significant.
Okay.
Sure. So this is my 2-minute SKA pitch. I mentioned to you that I'm the science director for a new $2 billion international telescope project called the Square Kilometer Array. Canada's been part of this initiative that's been in the design and pre-construction phase for almost 2 decades now. It takes a long time to build a $1 billion telescope with 10 different countries. And these are radio telescopes that will be sited in Australia and South Africa. And the idea is to cover or to use these new telescopes to address a number of fundamental issues that outstanding questions in astronomy today. So everything from, and I'll give a couple of words, and some of them might resonate with you, things like magnetic fields in the universe, pulsars, cosmology, transients, galaxy evolution, planet evolution, and gravitational waves. Those are all buzzwords that you've probably heard in the media recently. These are all areas of radio astronomy where Canada leads the world. And as a result, we're partners in this new telescope that will allow us to advance all of these fields for the next 50 or so years. So scientifically, Canada leads the world in a number of different areas. And technologically, it turns out that Canadians are the best in the world that build the things that make a telescope a telescope. In other words, it's the hardware that takes all of the signals from the different radio telescopes and multiplies them together to get an image of the sky. So that's called a correlator, and Canada is the top country in the world for building those correlators. And the plan is that we're going to build the correlator for the square kilometer array. We're going to take the hunk of metal and turn it into a telescope. And so technologically, that's really exciting. And that gives us lots of technological possibilities for technological return on investment for participation in the project. But it turns out that telescopes today are just as much supercomputers as they are pieces of metal. And so there's another piece to this puzzle, and it's to have the computational resources to actually scientifically exploit the data that comes down from the telescope. So to give you a sense of the scale here, when the telescope is built annually, we will need 240, just Canada will need 240 petabytes of computing capacity or of storage and 1.7 petaflops of computing capacity. That rivals the total compute and storage capacity in Canada for scientific research right now. This is a massive jump in the need for scientific data processing and storage capacity. And luckily, Canada is a leader in that respect as well. We have lots of experience handling scientific data. And the nice thing here is that there's a lot of overlap between the kinds of things you need to do for scientific data processing and other fields that contribute to the digital economy. So if you want to think about health for a minute, the kinds of security that you would need to put on health on data files for people's personal health records, as well as the kind of exercise that you undertake when you sift through an MRI to try and find a life-saving diagnosis in all of those data mirror very well to the kinds of exercises that we do when we're trying to scientifically exploit the data that comes from a telescope like the SKA. So Canada is positioning itself to participate in the construction and operation phases of the SKA, and with that is going to come a massive data compute demand. And as a country, we have a choice. We can take that money or that access and pay for it somewhere else, or we can develop a solution in Canada by Canadians, for Canadians, and for the rest of the world. And so what the Canadian astronomical community is advocating is that we have the capacity and the innovation to actually do this in Canada and make a Canadian science center for the SKA. And it's one of the things that we'll be requesting that be funded by government in the next little while as part of our contribution to the SKA. And so this is something that I'm deeply involved in, and it's something that an initiative like Dan's would fit very well within that broader picture and would really help to shape it would govern the shape of things to come for Canada in terms of astronomy, but also in terms of the broader digital economy. And so this is the beginning of potentially a really exciting phase in Canadian research and astronomy in particular.
Christine, thank you. So that concludes the demo and everything else that we, the main overview. I'd like